Welcome to Lab 11, Part 2, where we will find the error of the finite difference method as a function of the number of intervals n. I have copied and pasted the code of our last video on the finite difference method. In order to find the error as a function of n, I will need to make a new function whose input is n. So here I will define a function called error with the input of n. And then to include this code in my function, I will highlight the lines and then hit the tab key. I will also need this code in my function. I'll do a Ctrl X to cut and a Ctrl V to paste. Once again, I need to highlight and then hit tab. I will get rid of this line since our input is n. Next, I need to calculate the error of my solution list. To do that, I will need to take the difference between each of the values in my solution list and the exact value. So I will set that equal to error list, which will be a list of all of our errors, and the error will be the exact value dot the right hand side, then substituted with x equal to xs at I minus our approximation, which is the solutions list, indexed at us at I. Then we must cast this into a number using simpy.n, and then take the absolute value using abs, and the loop will be for I in range of n plus 1. And our function will return the maximum error in our error list. To do that, we will use return and then the max function and pass in our error list. Next, we will call our function with different n values to see how the error changes when increasing n. So here I will be using pandas, and our table will be two square brackets, where the first column will be our n, and our second value is the error at that n value. And n will be for n in range from 4 to 10. Then let's go ahead and display this as a PD data frame, where the table is t and the column names are n and error. And as you can see, the error decreases with increase in n. Now, because we use the centered finite difference, the absolute error should be proportional to the step size squared. We can test this by plotting the absolute error as a function of h. To graph this, we will be using matplotlib as PLT. Then we will need to generate our error table. So the first column here is h, which is 3 minus 0 divided by n. And our second column is the error at n, and for n in range of 4 to 15. Next, I will extract the x values from error table and set it equal to error table x using a list comprehension, and then point at 0 for point in error table. And then for the y values, I will copy and paste. Change this to y, and then the point at index 1. Now that we have our data, I will plot this as a scatter plot, pass in error table at x and error table at y, and then I will set the title equal to error versus h, where the x label will be h and the y label will be error. Finally, plot.show. Here you can see the graph, which looks to be quadratic. Now to check that this is actually quadratic, we will fit this to a quadratic curve using SciPy's curve fit function. As we said, the absolute error is directly proportional to h squared, which means we can fit the curve of absolute error equals to a times h squared, where a is a constant. To use SciPy's curve fit function, we will first import it from scipy.optimize import curve fit. And then I will also be needing numpy as np. First, we will declare our function f, which is the function we're fitting to, with the variable x and the constant a. Then I will cast x into a numpy array and return our function, which is a times x squared. Next, our curve fit function will return the coefficients as well as the covariance, which will be equal to curve fit, pass in our function f, and then the x and y values from our error versus h scatter plot, which is error table underscore x and error table underscore y. And then I will print the coefficient Next, I will calculate the r squared value. Recall from our previous videos, I will need to set y fit equal to f at error table underscore x, passing coefficient at 0. Then ssres is equal to numpy dot sum of error table underscore y minus y fit, all of this squared, and then ss tot equal to numpy dot sum of numpy dot array of error table underscore y minus numpy dot mean of error table underscore y, and all of this is squared. Finally, r squared will be equal to 1 minus ssres divided by ss tot, and I'll go ahead and print out our r squared value. So here you can see the coefficient is 4.158, which means the quadratic function is 4.158 times x squared, and the r squared value is 0.98. And then I will go ahead and plot our curve by first setting x values equal to numpy dot line space between 0 and 1.5. Then I will plot our function, which is x values, then call our function f, passing x values, and our a is the coefficient at 0. I will also plot our scatter plot from our previous graph, which is error table underscore x and error table underscore y. Once again, the title will be error versus h, the x label will be h, and the y label will be error, then plot.show. Here you can see both our line plot and our scatter plot are quadratic functions, which confirms that the absolute error is directly proportional to our step size squared.